Across the oceans, nothing appears to be changing. From above, the surface still carries the same quiet rhythm it always has. Waves fold into each other with familiar patterns. Light reflects in long, broken lines across open water. From a distance, the planet looks stable, complete, almost finished. Satellite images show vast blue expanses stretching uninterrupted between continents. There are no fractures, no sudden voids, no visible signs that anything fundamental is being lost. Even closer, standing at the edge of the sea, there is no immediate reason to question that impression. The horizon remains where it has always been. The tide rises and falls on schedule. The water still moves, still breathes, still gives the appearance of something steady and enduring. It is easy to assume that what we see reflects what is happening beneath. But the ocean has always been a place where appearance and reality separate quickly. The deeper you go, the less the surface tells you. Light fades, within the first few dozen meters, dissolving into a dim blue haze before disappearing entirely. Below that, everything continues, but not in a way that can be observed from above. Processes unfold without witnesses. Structures grow and decay without being seen. Entire ecosystems operate in silence, removed from the signals we rely on to understand change. This distance between what is visible and what is real is where the problem begins. Because when something changes in a place we cannot easily observe, it rarely announces itself in ways we recognize. There is no clear moment where one state ends and another begins. There is no single event that marks the transition. Instead, the change spreads slowly, distributed across time and space, subtle enough to avoid immediate attention, but persistent enough to reshape the system entirely. The ocean is undergoing that kind of change now, not through a sudden collapse, not through a single catastrophic failure, but through a gradual shift that does not present itself as a crisis. There is no single day when the ocean becomes something different. There is no clear boundary between before and after. What is happening is quieter than that. It is a process of reduction, of thinning, of systems losing complexity without losing form. From the outside, it still looks like an ocean, but what it contains, how it functions, and how much life it supports is slowly being altered. The difficulty is not just that this change is happening, but that it is happening in a way that avoids detection. Human perception is built to recognize sudden differences. We notice when something disappears overnight. We react when there is a clear disruption, when a system fails in a way that forces attention. But when change is incremental, when it unfolds over years or decades, it becomes much harder to hold on to a clear reference point. The ocean does not give us that reference point. Instead, it offers continuity. The surface remains intact. The cycles continue. The signals we expect from a failing system, noise, collapse, visible damage, are largely absent. What replaces them is something more difficult to interpret, a system that continues to function, but at a reduced capacity, with fewer interactions, fewer layers, fewer forms of life supporting one another. This is not the kind of change that produces headlines. There are no defining images that capture it fully, no single photograph that can communicate what has been lost. Because what is disappearing is not just individual species or isolated locations, but relationships, connections between organisms, structures that support entire communities, processes that have developed over centuries and are now weakening in ways that are not immediately visible. The ocean is not emptying, it is simplifying. And simplification, unlike destruction, does not feel urgent. A reef that loses half its species does not vanish. It remains in place, still recognizable, still functioning to some extent. Fish still move through it. Water still flows over it. To an untrained eye, it may even appear alive. But what is no longer there, the interactions, the diversity, the density of life, does not leave a clear absence. It leaves a quieter version of what existed before. This is the nature of systemic decline without spectacle. There is no single moment that demands attention. Instead, there is a slow accumulation of small changes, each one insufficient on its own to trigger alarm, but together forming a pattern that becomes undeniable only in hindsight. By the time that pattern is clear, the system has already shifted. The most dangerous changes are the ones that don't announce themselves, because they allow time for adaptation, not of the system itself, but of our expectations. As conditions shift, our understanding of what is normal shifts with them. Each generation inherits a slightly altered version of the world, and because there is no direct memory of what came before, the difference becomes difficult to measure. What once would have been recognized as loss becomes accepted as baseline. This is already happening in the ocean. Many of the changes now underway began decades ago, but they were not recognized as part of a larger pattern. They appeared as isolated events, local disturbances, temporary fluctuations. It is only over time, as these events repeat and intensify, that they begin to connect into something larger. But even then, the connection is not always obvious, because the system continues to operate just with less complexity than before. The ocean does not stop, it adjusts, and that adjustment can mask the extent of what is being lost. If a system collapses completely, it forces recognition. But if it continues in a diminished state, it allows for uncertainty. It creates space for interpretation, for doubt, for the assumption that what remains is sufficient. This is what makes the current transformation so difficult to confront. There is no clear boundary that separates a healthy ocean from a failing one. There is only a gradual shift along a spectrum, where each point looks similar to the last. From above, nothing looks different. But below, the structure of life is being altered in ways that are both measurable and, at the same time, easy to overlook. Entire ecosystems are losing their capacity to support the diversity they once held. Not all at once, and not everywhere simultaneously, but steadily enough that the overall trajectory is becoming clear. The ocean is not collapsing in a way that demands immediate attention. It is changing in a way that avoids it, and that is precisely why it matters, because a system that fails quietly is far more difficult to respond to than one that fails loudly. It does not trigger urgency. It does not create a clear moment of decision. It continues forward, carrying the appearance of stability while its underlying structure weakens. This is the paradox at the center of what is happening. The ocean still looks like the ocean, and that is what allows the change to continue. What makes this kind of change so difficult to grasp is not only that it happens beneath the surface, but that it unfolds in a way that does not match how we are built to understand the world. Human perception depends heavily on contrast. We notice differences when they are immediate, when one state clearly replaces another, when there is a before and an after that can be compared without effort. A forest that burns leaves behind a visible absence. A city that floods transforms overnight into something unrecognizable. These are events that force attention because they interrupt continuity. The ocean does not offer that kind of interruption. It changes within continuity, and continuity is easy to trust. When something appears stable from one moment to the next, the assumption is that it remains stable over longer periods as well. That assumption works reasonably well on land, where change is often visible and tied to specific events. In the ocean, it breaks down almost immediately. The scale is too large, the process is too slow, and the signals too diffuse. What is happening is not concentrated in one place or one time. It is spread across entire regions, across seasons, across years, so that no single observation captures it fully. Instead, each observation shows only a fragment, and that fragment on its own rarely looks alarming. This is where misinterpretation begins. A diver visiting a reef might still see fish moving through coral structures, still see colour, still see life. Without a clear memory of what that same reef looked like decades earlier, there is no obvious indication that anything has been lost. The reef appears intact, even if its complexity has been reduced, even if key species are missing, even if the underlying structure is weakening. The difference exists, but it does not present itself in a way that demands recognition. Over time, these small differences accumulate, but because they are experienced gradually, they are absorbed into our understanding of what is normal. This process has a name, though it is rarely discussed outside of scientific circles. It is called shifting baseline syndrome, and it describes the way each generation redefines normal conditions based on what they encounter, rather than what existed before. The baseline, the reference point for what is considered healthy or intact, shifts quietly with each passing decade. What was once abundant becomes rare, and then becomes expected as rare. What was once complex becomes simplified, and then becomes accepted as the standard form. The change is real, but the perception of change is lost. In the context of the ocean, this effect is particularly strong because direct experience is limited. Most people do not spend extended time observing marine ecosystems, and even those who do are often working within narrow timeframes. A scientist studying reefs over 10 or 20 years may detect patterns that others cannot, but even that span represents only a fraction of the time over which these systems developed. Coral reefs, for example, are built over centuries, sometimes millennia. Their full complexity is the result of long, uninterrupted accumulation of countless interactions layered over time. When that complexity begins to erode, the process does not reverse in a single moment. It unwinds gradually, and unless that unwinding is tracked carefully, it can pass unnoticed. Historical records provide some insight into how much has already changed. Early descriptions of coral reefs, written by explorers and naturalists, often describe environments so dense with life that the water itself seemed to move with organisms. Fish were not isolated individuals but continuous presence. Coral structures were not fragmented but expansive, forming intricate landscapes that supported a wide range of species. These accounts are sometimes dismissed as exaggeration, but when compared with modern data, they reveal a consistent pattern. What was once common is now exceptional. The difficulty is that we do not experience that contrast directly. We inherit the current state as our starting point, and without a clear reference to the past, it becomes difficult to recognize that anything is missing. This is not a failure of intelligence or awareness. It is a consequence of how perception works. The brain prioritizes immediate information, recent experiences, and visible changes. It is not designed to track slow, distributed transformations over long periods, especially in environments that are not constantly observed. The ocean exploits this limitation. Its changes are slow enough to avoid triggering alarm, but consistent enough to reshape entire systems over time. Another factor complicates this further. The ocean is not a single uniform system. It is composed of many interconnected regions, each responding differently to environmental pressures. Some areas show clear signs of stress, while others appear relatively stable. This variability can create the impression that problems are localized rather than systemic. If one reef is damaged but another remains intact, it is easy to assume that the system as a whole is resilient. But resilience has limits, and when similar patterns begin to appear across multiple regions, the underlying cause becomes harder to ignore. Even then, the distributed nature of the change makes it difficult to perceive as a single phenomenon. It does not present itself as a unified event, but as a series of smaller, disconnected observations. Warmer waters here, bleaching there, shifts in species composition elsewhere. Each of these can be explained individually, but together they form a pattern that points to a broader transformation. Recognizing that pattern requires stepping back, comparing data across time and space, and resisting the tendency to interpret each observation in isolation. This is what scientists have been doing, slowly building a picture of how the ocean is changing. But for most people, that broader perspective is not easily accessible. What remains is the immediate experience, and the immediate experience often suggests continuity rather than decline. This gap between scientific understanding and everyday perception is one of the reasons the current changes feel less urgent than they are. Without a clear, visible signal, it is difficult to generate a sense of scale or direction. The ocean continues to move, to reflect light, to support life, and those visible qualities reinforce the assumption that it remains fundamentally unchanged. But beneath that surface continuity, the baseline is shifting. Each year, each season, each small change adds to the cumulative effect, altering the system in ways that are not immediately apparent but become significant over time. The result is a form of normalization. Conditions that would have been considered degraded in the past are accepted as standard in the present. The absence of certain species, the reduction in diversity, the simplification of ecosystems, these are not always recognized as losses because there is no direct experience of what has been lost. Instead, they become part of the background, part of the expected state of the ocean. This is how decline can occur without being perceived as decline. It is not that the changes are invisible, but that they are interpreted within a shifting frame of reference. What we are seeing is real, but what we understand about what we are seeing is incomplete. The ocean is changing in ways that are measurable, documented, and increasingly difficult to reverse. But the perception of that change lags behind the reality, creating a situation where the system continues to degrade while appearing stable. We are not watching a sudden collapse. We're watching a slow transformation that is being absorbed into our definition of normal, one small adjustment at a time, until the difference between what was and what is becomes too large to ignore. But by then, the system has already moved on to something else. To understand what is actually being lost, it becomes necessary to look beyond the surface entirely, into the places where the structure of our ocean life is built and maintained. There are regions beneath the water that function less like isolated ecosystems and more like foundations, places where the density of interactions is so high that removing them affects everything connected to them. Coral reefs are one of those places, but they are often misunderstood because they are described in ways that emphasize appearance rather than function. They're called beautiful, vibrant, colorful, and while all of that is true, it obscures their real role. A coral reef is not simply a collection of organisms existing together in one location. It is a system that organizes life, concentrates it, and makes it possible at a scale that would not exist otherwise. Without reefs, large portions of the ocean would not become empty, but they would become structurally simpler, less capable of supporting the complexity that currently exists. This is why their importance cannot be measured by size alone. Coral reefs cover less than 1% of the ocean floor, yet they support roughly a quarter of all marine species. That ratio alone suggests something unusual is happening. It indicates that reefs are not just another habitat, but a kind of biological multiplier, a place where conditions allow life to diversify, interact, and expand far beyond what the surrounding environment would normally support. The reason for this lies in the way reefs function as physical and ecological structures at the same time. On a purely physical level, a reef creates complexity in space. Instead of a flat seabed, there are layers, crevices, overhangs, tunnels, and surfaces at every angle. This complexity provides shelter, reduces predation pressure, and creates microenvironments where different species can coexist without directly competing for the same resources. Small fish can occupy spaces that larger predators cannot reach. Invertebrates can attach themselves to surfaces protected from strong currents. Each layer of the reef becomes a niche, and each niche supports a different form of life. But the structure alone is not enough to explain the density of life found there. The reef also functions as a center of activity, a place where energy flows are concentrated and redistributed. Many marine species depend on reefs during critical stages of their lives. For some, reefs are breeding grounds, locations where adults gather to spawn in synchronized events tied to lunar cycles or seasonal changes. These events release massive quantities of eggs and sperm into the water, increasing the chances of survival in an environment where most offspring would otherwise be lost. For others, reefs serve as nurseries. Juvenile fish, too small and vulnerable to survive in open water, find protection within the reef structure. There, they can grow, feed, and develop until they are large enough to move into other parts of the ocean. Without this protected stage, many species would not reach adulthood in sufficient numbers to sustain their populations. The reef also acts as a buffer, both biologically and physically. It absorbs wave energy, reducing the impact of currents and storms on coastal areas. This creates calmer conditions behind the reef, allowing seagrass beds and other ecosystems to develop. These adjacent systems are often directly connected to the reef, forming networks where nutrients, organisms, and energy move between different environments. Fish that feed in open water may return to the reef for shelter. Species that begin life in the reef may migrate outward as they mature. The reef becomes a hub, not isolated but central to a wider system. This interconnectedness is what makes the loss of reefs so significant. When a reef degrades, the effects do not remain confined to that location. They spread outward, altering the dynamics of surrounding ecosystems. Fish populations decline not only because their habitat is lost, but because the entire network that supports their life cycle is disrupted. Species that rely on reefs for spawning or early development fail to reproduce successfully. Predators that depend on those species must either adapt, migrate, or decline themselves. The system does not collapse instantly, but it begins to unravel, one connection at a time. This process is difficult to observe directly because it does not produce a single visible outcome. Instead, it manifests as a gradual reduction in complexity. Fewer species are present. Interactions become less frequent. The system continues to function, but with less depth, less redundancy, less resilience. What was once a densely connected network becomes a simpler, more fragile structure. To see this clearly, it helps to consider what a reef looks like when it is fully intact. In those conditions, movement is constant. Fish of different sizes and species occupy different, layers of the water column. Some move in schools, coordinated and responsive to subtle changes in their environment. Others hover close to the coral, darting in and out of small openings. Invertebrates extend feeding structures into the water, capturing passing particles. Predators patrol the edges, maintaining a balance that prevents any one species from dominating. The entire system operates as a continuous exchange of energy, matter, and information. Now consider the same reef after it has been degraded. The structure may still be present, but it is less complex. Some of the smaller crevices have filled in with algae or sediment. The coral itself may be partially dead, its surface no longer supporting the same diversity of organisms. Fish are still present, but in lower numbers and fewer species. The patterns of movement are less dense, less coordinated. The system has not disappeared, but it has lost its intensity. It has become quieter, both visually and ecologically. This transition from complexity to simplicity is at the heart of what is happening in the ocean. Coral reefs are one of the clearest examples because their structure is so visible and their role so central, but the same pattern can be observed in other systems as well. The difference is that reefs make the change easier to detect if you know what to look for. They provide a reference point, a place where the contrast between what was and what is can still be measured. This is why their decline carries such weight. It is not just the loss of a particular type of habitat, it is the weakening of a system that supports a significant portion of ocean life. Remove that system and the effect propagate outward, altering the structure of the ocean itself. The water remains, the currents continue, but the underlying network that gives the ocean its richness and complexity begins to thin. What makes coral reef so structurally important becomes much clearer once you look closely at what coral actually is, because the word itself tends to suggest something passive, something more like a plant or a rock than a living system. That impression is misleading in a way that matters. Coral is not a surface that organisms live on. It is the organism, or more precisely, a colony of organisms, each one small enough to be overlooked on its own, but together capable of building structures large enough to be seen from space. At the smallest scale, a coral reef begins with individual units called polyps. Each polyp is a simple animal, soft-bodied, cylindrical, with a mouth surrounded by tentacles. It does not look like something that could construct anything lasting. It has no bones, no rigid frame, nothing that suggests permanence, but it has a process, and that process, repeated continuously over long periods, is what turns something fragile into something enduring. A polyp attaches itself to a surface and begins to secrete calcium carbonate, a mineral that forms a hard external skeleton. This skeleton is not shed or replaced. It remains in place, becoming part of the growing structure. As the polyp feeds, grows, and eventually reproduces, it creates genetically identical copies of itself, each one forming its own skeleton connected to the others. Over time, these colonies expand outward and upward, layer by layer, each generation building directly on top of the last. What begins as a thin coating becomes a branching form, then a network, then an entire reef. The process is slow, almost imperceptible in real time. Growth rates can be measured in millimeters per year. A structure that appears solid and permanent may represent centuries of continuous activity, each layer marking a period of stable conditions that allowed it to form. This is why reefs are often described as living architecture. They are not constructed in the way humans build structures, with a defined plan and a clear endpoint. They emerge through accumulation, through repetition, through the persistence of small actions over long periods. But the physical structure alone does not explain how coral sustains itself, especially in environments where nutrients are limited. In many tropical waters where reefs are found, the surrounding ocean can be relatively poor in the kind of nutrients that typically support dense biological communities. Yet reefs thrive in these conditions, supporting a level of diversity that seems out of proportion to what the environment should allow. The reason lies in a relationship that operates at a scale even smaller than the polyp itself. Within the tissues of each coral polyp live microscopic algae known as zooxanthellae. These algae are not external organisms drifting nearby. They are embedded within the coral, existing inside its cells, forming a partnership that is essential to the survival of both. The algae perform photosynthesis using sunlight to convert carbon dioxide and water into energy-rich compounds, primarily sugars. These sugars are then transferred to the coral, providing it with a steady supply of energy that allows it to grow, reproduce, and continue building its skeleton. In return, the coral provides the algae with protection and access to sunlight. It positions them in a stable environment where they can function efficiently, and it supplies them with the waste products they need for photosynthesis, including carbon dioxide and nutrients. This exchange is not occasional or optional, it is continuous and tightly integrated. The coral depends on the algae for the majority of its energy, and the algae depend on the coral for survival. Together they form a system that is more efficient than either could be alone. This is what allows reefs to exist in nutrient-poor waters. Instead of relying solely on external food sources, they generate energy internally through this symbiotic relationship. The reef, then, is not just a structure of calcium carbonate. It is a system of energy exchange, sustained by the constant interaction between coral and algae. This relationship also explains the color of coral reefs. The vibrant hues often associated with reefs come primarily from the pigments within the algae. The coral itself is translucent, its tissues allowing light to pass through to the algae inside. The color is not decoration. It is a visible indicator of the health and presence of this symbiotic system. When the algae are abundant and functioning, the reef appears rich and varied in color. When the relationship is disrupted, the color fades, revealing the white skeleton beneath. This connection between structure and energy is what makes coral reefs fundamentally different from other marine environments. They are not simply places where organisms gather. They are systems that actively produce the conditions necessary for life to concentrate and diversify. The physical complexity of the reef provides habitat, while the biological processes within the coral provide energy. Together, these elements create a feedback loop that supports a wide range of species, each interacting with the others in ways that reinforce the overall system. Fish feed on algae growing on the reef, preventing overgrowth that could smother the coral. Predators regulate the populations of smaller species, maintaining balance. Invertebrates recycle nutrients, keeping the system efficient. Each interaction contributes to the stability of the whole, but this stability is not absolute. It depends on the continued functioning of the underlying processes, particularly the relationship between coral and algae. If that relationship is disrupted, the energy flow that sustains the reef begins to break down. The structure may remain for a time, but without the energy input from the algae, the coral cannot maintain itself. Growth slows, reproduction declines, and the system becomes more vulnerable to external stresses. This is where the importance of understanding coral at its most basic level becomes clear. If reefs are seen only as physical structures, their loss might be interpreted as a form of erosion or damage that could be repaired or replaced. But if they are understood as systems built on specific biological interactions, then their loss represents something more complex. It is not just the removal of a structure, but the disruption of a process that took centuries to develop. The time scale matters. A reef that has grown over hundreds of years cannot be restored quickly, even if conditions improve. The accumulation of calcium carbonate, the establishment of symbiotic relationships, the development of ecological networks, all of these require stability over long periods. When that stability is interrupted, the system does not simply pause and resume. It begins to degrade, and the longer the disruption continues, the more difficult it becomes to return to its previous state. This is why reefs cannot be treated as static features of the ocean. They are dynamic, but their dynamics operate on timescales that are much longer than most human observations. What appears stable over a few years may be undergoing changes that only become apparent over decades. And because those changes are tied to the fundamental processes that sustain the reef, they have consequences that extend beyond the reef itself. Understanding coral as a living system of energy exchange and slow construction shifts the perspective from appearance to function. It reveals that what is at risk is not just a visible environment, but a set of processes that support a significant portion of marine life. When those processes begin to fail, the effects are not confined to a single location. They propagate through the network of interactions that depend on them, altering the structure of the ocean in ways that are both subtle and far-reaching. What makes this system particularly fragile is not immediately visible in the structure itself, but in the conditions it depends on, because the relationship between coral and algae only functions within a very narrow range of environmental stability, and that range is far tighter than most people would expect from something that appears so expansive and resilient. The reef looks solid, ancient, almost permanent, but the processes sustaining it operate on margins that leave very little room for variation. Temperature is one of the most critical of these margins. Coral reefs have evolved in waters that are remarkably consistent, typically within a range of about 23 to 29 degrees Celsius, and even within that range, stability matters more than the exact number. The system is not built to handle rapid change, it is tuned to continuity. When temperatures rise gradually over geological timescales, coral can adapt, migrate, or reorganize. But when temperatures shift even slightly over short periods, the response is not adaptation but stress. What is difficult to grasp is how small that shift needs to be. An increase of just 1 to 2 degrees Celsius above the usual seasonal maximum is often enough to trigger a physiological response in coral. Not a visible collapse, not an immediate breakdown, but the beginning of a process that unfolds internally before it becomes apparent externally. The coral, under thermal stress, begins to lose control of its relationship with the algae living inside it. The exact mechanisms are complex, involving changes in photosynthetic efficiency, the production of reactive oxygen species, and cellular damage, but the outcome is consistent. The coral expels the algae. It does not do this because the algae are no longer useful, but because under stress the relationship becomes harmful. The algae, instead of producing stable energy, begin to generate compounds that damage the coral cells. The partnership that once sustained the system becomes a source of risk. So the coral removes the algae, effectively shutting down the internal energy production that allowed it to thrive in nutrient-poor water. This is the moment that is often referred to as bleaching, because without the pigmented algae, the coral's translucent tissue reveals the white calcium carbonate skeleton beneath. But bleaching is not death. It is a stress response, a defensive reaction that can, under the right conditions, be reversed. If temperatures return to normal relatively quickly, the coral can re-establish its relationship with algae, either by reacquiring them from the surrounding water or by regrowing the remaining population within its tissues. Recovery is possible, but it is not guaranteed, and it depends heavily on how long the stress persists and how frequently it occurs. This is where the idea of a threshold becomes central. The system does not move smoothly from healthy to dead. It operates within a stable range, and once that range is exceeded, the response is not gradual decline but a shift into a different state. Below the threshold, the system maintains itself. Above it, the processes that sustain it begin to fail. The transition can be subtle at first. A reef may experience a mild bleaching event, lose some of its colour, and then recover. To an observer, this might appear as a temporary disturbance, something the system can handle. But each event leaves a mark. Recovery requires energy, and during recovery growth slows, reproduction decreases, and resilience is reduced. If another stress event occurs before full recovery is achieved, the system is weakened further. Over time, repeated crossings of this threshold accumulate, pushing the reef closer to a point where recovery is no longer possible. This is not because the coral suddenly loses its ability to survive, but because the conditions required for survival no longer exist consistently enough to support it. The threshold is not a single line, but a boundary that can shift depending on the history of the system. A reef that has experienced repeated stress may reach its breaking point at lower temperatures than it would have previously tolerated. This makes the process difficult to track and even more difficult to communicate because it does not present itself as a clear before and after scenario. Instead, it appears as a series of events, each one manageable on its own, but collectively leading to a change that is far more significant than any individual event would suggest. The broader context of ocean warming adds another layer to this dynamic. Global sea surface temperatures have been increasing over the past century, with more pronounced changes in recent decades. The average increase may seem modest when expressed as a global figure, often described in fractions of a degree, but the impact on systems like coral reefs is not determined by the average. It is determined by extremes, by how often and how long temperatures exceed the thresholds that trigger stress responses. Marine heat waves, periods of unusually high ocean temperatures, have become more frequent and more intense. These events can last for weeks or months, exposing reefs to conditions that exceed their tolerance for extended periods. During such events, bleaching can occur on a large scale, affecting entire reef systems across regions or even globally. The first global bleaching event recorded in the late 20th century was considered unusual. Subsequent events have become more common, with shorter intervals between them, reducing the time available for recovery. What makes this particularly challenging to perceive is that the ocean does not display these changes in a way that aligns with how humans typically interpret environmental shifts. On land, a change of a few degrees can be felt directly. It alters daily experience, influences behavior, and is easily noticed. In the ocean, especially at the surface, these changes are less obvious. The water may feel slightly warmer, but without a point of comparison, it is difficult to recognize the significance of that difference. Beneath the surface, where the critical interactions occur, the changes are invisible to most observers. The reef may look intact from above, the water may appear clear, and the absence of immediate dramatic transformation can give the impression that the system remains stable. But the threshold has already been crossed. The stress response has begun, and the processes that sustain the reef are already being altered. This is why the concept of thresholds introduces a form of tension that is not based on spectacle, but on timing. The system does not announce when it is approaching its limits. It does not provide clear signals that align with human attention. Instead, it continues to function, to appear stable, even as the conditions that support that stability are being eroded. By the time visible signs become widespread, the underlying processes have already been disrupted for some time. The challenge, then, is not just understanding that thresholds exist, but recognizing that they are being approached and crossed without clear markers. The reef does not collapse in a single moment. It transitions, often quietly, from a state of growth and resilience to one of vulnerability and decline. And because this transition is driven by conditions that change gradually and unevenly across the ocean, it does not occur everywhere at once. Some reefs may still appear healthy, others may be in recovery, and others may have already crossed into a state where recovery is unlikely. This patchwork of conditions makes it even harder to perceive the overall trajectory. It allows for the possibility of focusing on areas that remain intact and interpreting them as representative of the whole, while overlooking the broader pattern of change. The moment the algae are expelled, the reef does not collapse, and that is precisely what makes the process so difficult to interpret correctly. Because what follows is not immediate destruction, but a shift into a state that can still resemble life from a distance, even while the underlying system has already begun to fail. The coral remains physically intact, its structure unchanged, its presence still anchoring the surrounding ecosystem. But internally, the conditions that sustained it have been fundamentally altered. Without the algae, the coral loses its primary source of energy, the steady stream of sugars produced through photosynthesis that once fueled its growth, repair, and reproduction. What remains is a far less efficient method of survival, one that relies on capturing microscopic particles from the water column, plankton, and organic debris through the extension of its tentacles. This form of feeding has always been part of the coral's biology, but it was never designed to sustain the organism on its own. It is supplemental, not foundational. When the algae are gone, the coral is forced to rely on this limited pathway, effectively shifting from an energy-rich system to one operating under scarcity. The change is immediate at a metabolic level, even if it is not yet visible externally. Growth slows first. The process of building the calcium carbonate skeleton, which defines the reef structure, becomes less active as energy is redirected toward basic survival. Reproduction is reduced, both in terms of frequency and success, because the organism no longer has the surplus energy required to produce and release gametes into the water. Repair mechanisms, which normally address minor damage from currents, grazing fish, or environmental fluctuations, become less effective. Small injuries that would once have healed quickly begin to persist, creating entry points for disease and further degradation. The coral is still alive, but it is no longer functioning as it did before. This state can persist for some time, depending on the severity and duration of the stress that caused the bleaching. In cases where temperatures return to normal relatively quickly, the coral may begin to recover. Algae can be reacquired, either from remnants within the coral's tissues or from the surrounding environment, and the symbiotic relationship can be re-established. The system can, in a sense, rebuild itself from within, restoring the flow of energy that allows the reef to grow and sustain the complex web of life around it. But this recovery is not instantaneous, and it is not guaranteed. It depends on a window of stability that is becoming increasingly rare. If the elevated temperatures persist, or if another stress event follows before recovery is complete, the coral remains in this energy-deprived state for longer, and the consequences begin to accumulate. Starvation does not occur as a sudden event. It unfolds gradually as the imbalance between energy intake and energy demand widens. The coral continues to expend energy simply to maintain its basic functions, to keep its cells alive, to regulate its internal processes, but without sufficient input, it begins to draw on its reserves. These reserves are limited, and once they are depleted, the organism cannot sustain itself. Tissue begins to thin, then to recede, exposing more of the underlying skeleton. The coral may appear intact from a distance, but at closer range, the signs of decline become evident. Areas of the colony lose their living tissue entirely, leaving behind bare white surfaces that no longer support the intricate interactions that once defined the reef. At this stage, the process becomes increasingly difficult to reverse. Even if conditions improve, the coral may no longer have the capacity to recover fully, as too much of its living structure has been lost. What makes this progression particularly significant is that it is not driven by a single, catastrophic event, but by the persistence of conditions that exceed the system's tolerance. The initial act of bleaching is, in itself, a survival mechanism, a way for the coral to protect itself from the immediate damage caused by stressed algae. But that mechanism is only effective if the stress is temporary. When the stress becomes prolonged or recurrent, the same response that once served as protection becomes the first step toward decline. The coral does not have an alternative strategy. It cannot choose to retain the algae under harmful conditions, because that would lead to cellular damage and potentially faster death. It cannot sustain itself indefinitely without the algae, because its energy requirements exceed what it can obtain through feeding alone. The system is constrained by its own design, optimized for stability, but vulnerable to change. This is where the concept of inevitability begins to emerge, not as a dramatic conclusion, but as a logical outcome of the processes already in motion. If the conditions that trigger bleaching occur more frequently than the system can recover from, then each event reduces the resilience of the reef, making it more susceptible to the next. Over time, the balance shifts. What was once a rare disturbance becomes a regular occurrence, and the periods of recovery become shorter and less effective. The coral spends more time in a state of stress than in a state of growth, and the cumulative effect is a gradual reduction in the overall health of the system. This is not always immediately visible at the scale of individual colonies or even entire reefs, because different parts of the system may respond differently, and some areas may retain their colour and structure longer than others. But at a larger scale, the pattern becomes clearer. Regions that once supported extensive, thriving reefs begin to show signs of widespread bleaching, followed by partial or complete mortality. The complexity of the reef diminishes as the living components that created its structure are lost. Fish populations change as species that depended on the reef for shelter or food are forced to move or decline. The entire system begins to reorganize, not toward a new equilibrium that maintains the same level of biodiversity and function, but toward a simpler state, one that can exist under the new conditions but does not provide the same ecological support. The transformation is not abrupt, and it does not produce a single moment that can be identified as the point of collapse. Instead, it is a sequence of responses, each one consistent with the biology of the system, each one predictable when viewed in isolation, but collectively leading to a change that is far more significant than any individual step would suggest. The bleaching event, which might initially be interpreted as a temporary disturbance, becomes part of a larger pattern, one in which the mechanisms of survival are gradually overwhelmed by the persistence of stress. What follows after the processes that weaken and eventually kill coral is not an empty space, not an immediate disappearance of the reef, but a transformation that is subtle in its progression and deeply misleading in its appearance, because the structure remains long after the living system that built it has faded. From a distance, a dead reef can still look like a reef. The contours are still there, the shapes still rise from the seafloor, the outlines of what was once a complex ecosystem remain visible. But the difference is not in the silhouette, it is in the detail, in the density, in the activity that once filled every available surface and layer of that structure. A living reef is not just a formation, it is a system in constant motion, defined by interactions that occur simultaneously at multiple scales. Fish move in coordinated patterns, grazing, hunting, sheltering. Invertebrates occupy the smallest crevices, filtering water, recycling nutrients, maintaining the balance of the system. The coral itself is active, its polyps extending and retracting, feeding, building, responding to the environment. Even the water around a healthy reef behaves differently, shaped by the presence of life that influences currents, nutrient distribution, and chemical exchanges. This complexity creates a kind of density that is not only visual but functional. Every part of the reef is used, occupied, contributing to the overall system. When that system begins to fail, the change does not remove the structure immediately. Instead, it removes the processes that gave that structure meaning. The first visible shift often appears as a loss of colour, the vibrant range of hues that once defined the reef, fading into pale or stark white as bleaching progresses. If the coral dies, this white does not remain pristine for long. The exposed skeleton becomes a surface for other organisms, particularly algae, to colonize. Without the living coral to maintain dominance over the substrate, algae begin to grow first in patches, then more extensively, covering the surfaces that were once occupied by coral tissue. This transition is not random. It reflects a change in the balance of the ecosystem. In a healthy reef, herbivorous fish and invertebrates keep algal growth in check, preventing it from overwhelming the coral. But as the coral declines and the structure of the reef changes, these populations can also decrease, either because they lose habitat or because the broader system no longer supports them in the same way. With fewer grazers, algae can spread more freely, further inhibiting any potential recovery of coral by occupying the space that new coral larvae would need to settle and grow. The reef begins to shift from a coral-dominated system to one dominated by algae, a transition that represents not just a change in appearance, but a fundamental alteration of the ecosystem's function. The structural complexity of the reef also begins to degrade over time. Coral skeletons, once maintained and reinforced by living tissue, become more vulnerable to physical and biological erosion. Waves, currents, and storms gradually break down the brittle structures. Boring organisms, such as certain types of sponges and mollusks, penetrate the skeleton, weakening it from within. Without the continuous process of growth that living coral provides, the balance between construction and erosion is lost, and the reef begins to flatten. This reduction in structural complexity has cascading effects. The intricate network of crevices and overhangs that once provided shelter for countless species becomes simplified, reducing the number of niches available. Fish that relied on these structures for protection from predators or for breeding may leave or decline in number. Species that depended on the coral itself for food or habitat disappear. The diversity of life that characterized the reef diminishes, not always through dramatic die-offs, but through gradual absence. Fewer species, fewer individuals, fewer interactions. The system becomes quieter in a biological sense, even if it is not immediately apparent to a casual observer. One of the less visible but equally significant changes occurs in the soundscape of the reef. Healthy reefs are not silent environments. They produce a constant background of sound generated by the activities of the organisms that inhabit them. Fish create noises through movement, feeding, and communication. Invertebrates, such as snapping shrimp, produce sharp, frequent clicks that contribute to a complex acoustic environment. This soundscape is not incidental. It plays a role in the behavior of marine organisms, including the settlement of larvae, which can use sound cues to locate suitable habitats. As the reef declines, this acoustic complexity diminishes. The reduction in species diversity and activity leads to a quieter environment, one that lacks the signals that once indicated a thriving ecosystem. This change is rarely perceived directly by humans, but it is measurable and has implications for how the system functions and how it might recover. The absence of sound becomes another layer of simplification, reinforcing the shift away from a dynamic, interconnected system towards something more static and less capable of supporting life. What is important to understand is that this transformation does not present itself as a single, defining moment of loss. There is no point at which the reef simply disappears. Instead, it becomes something else, something that retains the outline of what it once was but lacks the processes that made it a living system. This can create a false sense of continuity. To someone unfamiliar with the details, a dead or degraded reef might still appear as a natural functioning part of the ocean. The water is still there, the structure is still visible, some fish may still be present. But the density, the diversity, the interactions that defined the original system are reduced. The reef is no longer performing the roles it once did, no longer providing the same level of support to the broader ecosystem. It has been simplified, not removed. This simplification is the key to understanding what death means in this context. It is not an abrupt end, but a reduction in complexity, a loss of layers, interactions, and functions that once made the system robust. The process is incremental, often uneven, and therefore easy to overlook. But as it progresses, the cumulative effect becomes significant, altering not just individual reefs but the larger systems they are part of. What becomes increasingly clear when looking closely at these systems is that nothing about their decline follows the pattern people instinctively expect from the word collapse. Because collapse suggests a moment, a break, a clear boundary between before and after, and what unfolds in the ocean does not offer that kind of clarity. Instead, it moves through cycles that can look, at least temporarily, like stability returning, even as the underlying capacity of the system is being reduced with each repetition. A reef may bleach during a period of elevated temperature, lose part of its living tissue, and then, as conditions ease, begin to recover. Colour returns in patches, algae symbiosis is re-established. Fish activity increases again, and for a time the system appears to regain its function. From a distance or over short observational windows, this can be interpreted as resilience, as evidence that the system can absorb disturbance and return to its original state, and in a limited sense, that interpretation is not entirely wrong. Coral reefs do have the capacity to recover from stress. They have done so for millions of years, through natural fluctuations in climate and environmental conditions. But the critical difference now lies in the frequency and intensity of those disturbances. Recovery is not just about the ability to regrow or recolonize, it is about time. It requires a period in which the system can operate without being pushed beyond its limits, allowing energy reserves to be rebuilt, structures to be repaired, and reproductive cycles to proceed without interruption. When that period is shortened, when the next disturbance arrives before the system has fully recovered from the previous one, the baseline shifts. The reef does not return to its original state. It returns to a slightly diminished version of it. This is the beginning of a cycle that does not reset completely. Each bleaching event, each period of stress, leaves behind subtle changes. Some coral colonies may not recover at all, reducing the overall coverage of living coral. Others may recover partially, but with reduced growth rates or weakened structures. The composition of species can change, with more resilient but less structurally complex species becoming dominant, altering the architecture of the reef. Fish populations adjust in response to these changes, sometimes declining, sometimes shifting towards species that can tolerate the new conditions, but do not perform the same ecological roles. The system remains active, but it is no longer the same system. When the next cycle of stress occurs, it acts on this altered baseline. The reef is now less resilient than it was before, less capable of absorbing the disturbance and returning to a previous state. The impact of the same level of stress is therefore greater, not because the stress itself has changed, but because the system it is acting upon has been weakened. This creates a compounding effect. Each cycle does not simply add damage in a linear way. It reduces the system's ability to cope with future stress, accelerating the trajectory of decline. What makes this process particularly difficult to perceive is that it does not produce a consistent visual narrative. Some areas may appear to recover well after a bleaching event, showing signs of regrowth and activity, while others may decline more rapidly. This spatial variability can give the impression that the system as a whole is more stable than it actually is, because the areas that are recovering are more visible or more frequently observed. Meanwhile, the areas that are not recovering, or that have already transitioned to a degraded state, may be less prominent or less accessible. Over time, however, the pattern becomes more coherent. The intervals between major bleaching events shorten, the extent of those events increases, and the proportion of reefs that fail to recover grows. The cycles begin to overlap, with some reefs entering a new period of stress before they have exited the previous one. In this context, the idea of a tipping point emerges not as a sudden threshold that is crossed in a single moment, but as the cumulative result of these overlapping cycles. The tipping point is reached when the system can no longer return to a state that resembles its previous condition, not because of a single catastrophic event, but because the accumulated changes have altered its structure and function to such an extent that recovery, as it once occurred, is no longer possible. At this stage, the system may still persist, but in a fundamentally different form. Coral cover may be significantly reduced, structural complexity diminished, and biodiversity lower. The processes that once maintained the reef's growth and resilience are replaced by processes that maintain a simpler, more degraded state. This transition can be stable in its own way, meaning that the system does not continue to decline indefinitely, but instead settles into a new equilibrium. However, this new equilibrium does not provide the same ecological functions or support the same level of life as the original reef system. It represents a loss that is not immediately obvious because it is not defined by absence alone, but by the reduction of what was once there. The cumulative nature of this process also means that there is no single moment at which it becomes visible to everyone. Different observers, looking at different parts of the system or at different times, may come to different conclusions about its state. Some may see recovery and interpret it as resilience. Others may see decline and interpret it as collapse. Both observations can be accurate within their specific contexts, but neither captures the full trajectory of the system. To understand that trajectory requires a longer view, one that considers not just individual events, but the pattern they form over time. It requires recognizing that each cycle of stress and partial recovery is not a reset, but a step along a path that leads away from the original state of the system. The absence of a single defining moment of collapse makes it easier to overlook this path, to interpret the system as fluctuating rather than declining. But the direction of change becomes clear when the cycles are viewed together, when the gradual reduction in resilience, complexity, and function is understood as a continuous process rather than a series of isolated events. As the structure of the reef begins to simplify, the consequences do not remain confined to the coral itself, because what the reef provides is not just a surface for organisms to attach to, but a framework within which entire networks of relationships are organized. And when that framework is altered, the effects propagate outward through layers of the ecosystem that are not always immediately connected in obvious ways. The first changes are often seen in species that depend directly on the coral for shelter or food. Many fish are not simply associated with reefs in a general sense, but are tied to specific types of coral, using particular formations for protection from predators or for nesting and reproduction. When those corals die or degrade, these fish do not have equivalent alternatives readily available. The complexity of the reef, the intricate arrangement of branches, crevices, and overhangs, is not easily replicated by other structures. As that complexity diminishes, the available habitat contracts. Fish that once occupied specific niches within the reef may be forced to move if suitable habitat exists elsewhere, or they may decline if it does not. This initial shift can appear as a change in composition rather than a reduction, with some species becoming less common while others, often more generalist species, become more dominant. But this is only the first layer of change. As herbivorous fish decline or redistribute, their role in controlling algal growth is weakened. Algae, already expanding due to the absence of living coral, encounter less resistance and can spread more rapidly, further altering the physical and chemical environment of the reef. This, in turn, affects other species that rely on the balance between coral and algae, creating a feedback loop that reinforces the new state of the system. The changes continue upward through the food web. Predatory fish, which depend on smaller fish and invertebrates for food, begin to experience shifts in their own populations as their prey becomes less abundant or more difficult to find. Some predators may adapt by expanding their range or altering their diet, but others may decline if the changes outpace their ability to adjust. The relationships between species, built over long periods of coevolution, are disrupted, not necessarily in a way that leads to immediate collapse, but in a way that reduces the stability of the system. Interactions that once maintained balance become less predictable, and the system becomes more susceptible to further disturbances. It is important to understand that these relationships are not linear. The reef is not a simple chain of cause and effect, but a network of interconnected systems, each with its own dynamics, layered together in a way that allows the whole to function. There are mutualistic relationships, like the one between coral and algae, but also between fish and the reef, where fish contribute to the maintenance of the system through grazing, nutrient cycling, and other processes. There are competitive relationships, where species vie for space and resources, and these competitions are influenced by the structure of the reef itself. There are predator-prey relationships that regulate populations and prevent any single species from dominating. When the reef begins to degrade, these layers do not unravel all at once. They shift, adjust, and in some cases temporarily stabilize in new configurations. But the overall effect is a reduction in the number of functional connections within the system. Fewer species, fewer interactions, fewer pathways through which energy and nutrients can move. This reduction in connectivity makes the system less resilient, less able to absorb shocks and maintain its function. One way to think about this is to consider the reef as a series of overlapping systems, each dependent on the others. The structural system, built by the coral, provides the physical space. The biological system, composed of the organisms that inhabit that space, creates the interactions that define the ecosystem. The chemical system, involving the exchange of nutrients and energy, supports the biological processes. When the structural system is compromised, the biological system is constrained, and when the biological system changes, the chemical processes are altered. These changes feed back into the structural system, influencing the ability of coral to grow or recover. The result is not a single chain reaction, but multiple reactions occurring simultaneously, each influencing the others. As these processes continue, the composition of the reef community can shift towards species that are more tolerant of the altered conditions, but that do not contribute to the same level of structural or functional complexity. For example, certain types of algae or less complex invertebrates may dominate areas where coral once thrived. These organisms can maintain a form of biological activity, but they do not build the three-dimensional structures that coral does, nor do they support the same diversity of species. The ecosystem becomes simpler, not empty, but reduced in its capacity to support life at the same scale and diversity as before. This simplification has implications beyond the immediate boundaries of the reef. Reefs are often connected to other marine systems, such as seagrass beds and mangroves, through the movement of species and the flow of nutrients. Changes in the reef can therefore influence these adjacent systems, altering migration patterns, feeding behaviors, and the distribution of organisms across larger areas. The effects can extend further still, influencing fisheries, coastal protection, and other services that humans derive from these ecosystems. But within the reef itself, the most significant change is the loss of the layered complexity that once defined it. The system does not cease to exist, but it becomes something else, something with fewer connections, fewer interactions, and less capacity to sustain the diversity of life that once depended on it. Running beneath all of these visible changes is another process that does not announce itself in color or structure, but alters the conditions of the entire system at a chemical level, changing the very medium in which all marine life exists. And unlike temperature, which can be felt and measured in ways that are intuitive, this shift is almost entirely invisible without instrumentation, yet it operates continuously, affecting every organism that depends on the ocean's chemistry to maintain its internal balance. The ocean has always acted as a vast buffer for the planet, absorbing a significant portion of the carbon dioxide released into the atmosphere. When CO2 enters seawater, it does not simply dissolve and remain unchanged. It reacts with water to form carbonic acid, which then dissociates into bicarbonate ions and hydrogen ions. This increase in hydrogen ions is what lowers the pH of the water, making it more acidic. The change in pH over the past century may seem small when, expressed numerically, a fraction of a unit, but the pH scale is logarithmic, meaning that even slight shifts represent significant changes in acidity. More importantly, the consequences of this shift are not uniform across all aspects of the ocean, but are particularly impactful for organisms that rely on carbonate ions to build their shells and skeletons. Coral is one of these organisms. its ability to construct the calcium carbonate framework that defines the reef depends on the availability of carbonate ions in the surrounding water. As the concentration of hydrogen ions increases, they bind with carbonate ions to form bicarbonate, reducing the amount of carbonate available for calcification. This does not stop the process of skeleton formation entirely, but it makes it more difficult and energetically costly. Coral must expend more energy to extract the necessary materials from the water, and even then, the structures it builds may be less dense or more fragile. This effect compounds the stress already imposed by rising temperatures. A coral that has survived bleaching, that has managed to re-establish its symbiotic relationship with algae and resume its basic functions, does not return to the same conditions it experienced before. The chemical environment has shifted in a way that makes every subsequent act of growth more demanding. The reef continues to exist, but its capacity to rebuild, to repair damage, and to maintain its structural integrity is gradually reduced. This has implications not only for the coral itself, but for all the organisms that depend on the reef's physical structure. As the skeleton becomes more susceptible to erosion, the balance between growth and breakdown shifts further toward loss. What is being built is less robust, and what is being eroded is not replaced at the same rate. Over time, this contributes to the flattening and simplification of the reef, reinforcing the changes already driven by biological and thermal stress. The impact of ocean acidification extends beyond coral to a wide range of marine organisms, including those that form shells, such as mollusks, and those that play critical roles in the base of the food web, such as certain types of plankton. These organisms also rely on carbonate ions to build their structures, and as those ions become less available, their ability to grow and reproduce can be affected. In some cases, shells may become thinner or more prone to damage, increasing vulnerability to predation and environmental stress. Because these organisms occupy foundational positions in the ecosystem, changes in their populations can have cascading effects, influencing species that depend on them for food and altering the flow of energy through the system. The combined effect of warming and acidification creates a situation in which multiple stresses act simultaneously, each one amplifying the impact of the others. Temperature stress can weaken coral, making it more susceptible to disease and reducing its ability to recover from bleaching. Acidification can reduce the efficiency of calcification, making it harder for coral to maintain its structure. Together, these processes do not simply add their effects, they interact in ways that can accelerate the overall decline of the system. A coral that might have survived a temperature increase under previous chemical conditions may now struggle to do so, because the additional stress of acidification reduces its margin for survival. This interaction is another reason why the changes in the ocean are difficult to interpret through isolated observations. It is not a single factor that drives the transformation of the reef, but the convergence of multiple processes, each operating on its own timeline but intersecting in ways that shape the overall outcome. The chemical shift in the ocean does not produce a visible event like bleaching, but it alters the background conditions against which all other events occur. It changes the baseline, making it more difficult for the system to return to its previous state, even when other stresses are temporarily reduced. This creates a form of long-term pressure that is less dramatic but equally significant. The reef is not only dealing with episodic disturbances such as heat waves, but with a continuous change in the environment that underpins its existence. Over time, this continuous pressure can lead to a gradual weakening of the system, even in the absence of major events. Corals may grow more slowly, reproduce less effectively, and build structures that are more vulnerable to damage. The ecosystem, already simplified by the loss of species and interactions, becomes further constrained by the limitations imposed by its chemical environment. This is not a process that produces immediate visible collapse, but one that steadily reduces the capacity of the system to sustain itself. It operates in the background, often unnoticed, yet it influences every aspect of the reef's function and its ability to respond to other forms of stress. What begins to emerge from all of these overlapping changes is a pattern that is easy to misinterpret if it is viewed only through the lens of presence or absence, because the ocean does not become empty in the way people often imagine environmental loss. It does not turn into a void or a lifeless expanse. Instead, it continues to hold life, sometimes in forms that are still abundant, still active, still visible, but the nature of that life shifts in ways that reduce the overall complexity of the system, and it is this reduction that defines what is happening far more accurately than any notion of complete disappearance. In many areas where coral has declined or disappeared, life does not vanish, it reorganizes. Algae, which were once kept in balance by coral dominance and herbivory, expand and take over available surfaces. Certain species of fish that can tolerate a wider range of conditions remain, or even increase in number, while more specialized species decline or disappear. Microbial communities, often overlooked because they are not directly visible, can become more dominant, altering the chemical processes within the water. The system continues to function in a basic sense. Energy still flows, organisms still interact, but the diversity of those interactions is reduced. Where there were once many overlapping pathways for energy and nutrients to move through the ecosystem, there are now fewer, more simplified routes. This shift towards simplicity is not random. It reflects a selection process driven by the changing conditions of the environment. Species that require stable, narrow conditions that depend on specific relationships or structures are more vulnerable to change and therefore more likely to decline. Species that are more flexible, that can tolerate a wider range of temperatures, chemical conditions, or habitat types, are more likely to persist. Over time, this leads to a community composed increasingly of generalist organisms that can survive under a variety of conditions but that do not create or maintain the same level of structural or functional complexity as the original system. The result is an ecosystem that is still active but less intricate, less layered, and less capable of supporting a wide range of life. In coral reef systems, this often manifests as a transition from coral-dominated environments to algae-dominated ones. The reef structure, once built and maintained by living coral, becomes covered in macroalgae, which can grow rapidly and occupy large areas. These algae provide some habitat and food for certain species, but they do not replicate the three-dimensional complexity of coral structures, nor do they support the same diversity of organisms. Fish communities shift accordingly. Species that relied on coral for shelter or feeding may disappear, while those that can utilize algae or more open habitats may remain. The visual impression may still be one of life, of movement and activity, but the underlying system has changed in a way that reduces its overall capacity. This pattern is not limited to coral reefs. In other parts of the ocean, similar processes can be observed. In areas affected by overfishing, for example, the removal of top predators can lead to increases in smaller, more opportunistic species, altering the structure of the food web. In regions experiencing changes in temperature or chemistry, plankton communities can shift towards species that are better adapted to the new conditions, influencing the entire marine food chain. These changes do not eliminate life, but they simplify the systems in which that life exists. One of the reasons this simplification is difficult to recognize is that human perception is often drawn to the presence of activity rather than the structure of the system that supports it. If fish are still visible, if the water still appears clear, if there is still movement and colour, it is easy to assume that the system is functioning as it should. But activity alone does not indicate health or complexity. A simplified system can still be active, just as a degraded forest can still contain trees and animals. The difference lies in the diversity of interactions, the range of species, and the capacity of the system to sustain itself over time and to respond to further changes. As complexity decreases, so does resilience. A system with many species and many interactions has multiple pathways through which it can adapt to disturbances. If one species declines, others may fill its role, maintaining the overall function of the ecosystem. In a simplified system, these alternative pathways are reduced. The loss of a single species or function can have a more pronounced impact because there are fewer substitutes available. This makes the system more vulnerable to additional stress, creating a feedback loop in which simplification leads to reduced resilience, which in turn makes further simplification more likely. The ocean, then, is not transitioning from a state of life to a state of absence, but from a state of high complexity to one of lower complexity. It is becoming more uniform, more dominated by a smaller number of species that can tolerate the changing conditions. This uniformity can mask the extent of the change because it does not present itself as emptiness. Instead, it presents as continuity with subtle differences that require a deeper understanding of the system to fully appreciate. The loss is not in the existence of life itself, but in the richness and diversity of that life, in the intricate web of relationships that once defined the ecosystem. As those relationships are reduced, the system becomes simpler, and in that simplicity, it loses much of what made it resilient and capable of supporting a wide range of species. And yet, despite the scale of these changes and the depth at which they reshape entire ecosystems, most people will never encounter them in a way that feels immediate or undeniable, because the conditions that define how humans perceive change are almost perfectly misaligned with the way these processes unfold in the ocean, creating a gap between reality and recognition that allows the transformation to continue largely unnoticed. Human perception is built around contrast, speed, and proximity. We notice things when they change quickly, when the difference between before and after is clear, and when those changes occur within our direct experience. A forest fire, a storm, a sudden die-off on land. These are events that produce immediate visible disruption. They create a moment that can be identified, documented, and remembered. The ocean does not operate in that way. Its changes are often gradual, distributed across vast areas, and hidden beneath a surface that reveals very little of what is happening below. Even when significant transformations are underway, the surface can appear stable, the horizon unchanged, the water reflecting the same light it always has. Without specialized equipment or direct immersion, the processes that define the state of the ocean remain out of view. This distance is not only physical but also sensory. Humans do not have a natural way to perceive subtle changes in water temperature, chemistry, or biological composition over time, especially when those changes occur below the surface. A diver who returns to the same reef after several years may notice differences, a reduction in coral cover, a shift in fish populations, a change in colour and texture, but even then the perception is shaped by memory, which itself is subject to distortion and normalization. For those who do not have repeated direct contact with these environments, the changes are even harder to grasp. The ocean becomes an abstract concept rather than a lived experience, and abstract changes are easier to overlook or misunderstand. Geography adds another layer to this disconnect. Many of the most affected reef systems are located far from the daily lives of the majority of the global population, often in tropical regions that are visited only occasionally, if at all, by those who consume information about them. This creates a situation in which the areas undergoing the most significant changes are also those that are least directly observed by the people who might otherwise respond to them. The impact becomes something that happens elsewhere, to places that are not part of everyday experience. Without a sense of proximity, the urgency of the change is diminished, not because the change is less significant, but because it does not intersect with daily perception in a way that demands attention. Media representation further shapes this perception. The way information is communicated tends to favour events that can be captured as moments, as clear narratives with a beginning, middle and end. Sudden disasters, dramatic visuals and immediate consequences are more easily conveyed and more likely to engage attention. The slow transformation of a coral reef, the gradual shift in species composition, the incremental changes in ocean chemistry do not fit neatly into this framework. They lack a single, defining image that encapsulates the process. A bleached reef can be photographed, a comparison between past and present can be shown, but the full extent of the change, the accumulation of cycles, the underlying processes, are more difficult to represent in a way that resonates quickly. As a result, these stories are often simplified or fragmented, presented as isolated events rather than as parts of a continuous trajectory. This fragmentation reinforces the perception that what is happening is temporary or localized rather than systemic. There is also a psychological component that influences how gradual change is interpreted. Humans tend to adapt their expectations based on what they experience over time, a process that allows for stability in perception but can also obscure long-term trends. When changes occur slowly, each new state becomes the reference point for what is considered normal. A reef that has already lost a portion of its coral may be perceived as healthy by someone encountering it for the first time, because there is no direct experience of what it was like before. Even for those who have observed the reef over time, the incremental nature of the change can make it difficult to recognize the full extent of the transformation. Each step may seem manageable, each shift explainable, and without a clear moment of rupture, the overall trajectory can be underestimated. This creates a situation in which decline is not only happening, but being continuously redefined as normal. The absence of a single moment of collapse plays a central role in this dynamic. Without a clear boundary between a functioning system and a failed one, there's no point at which recognition becomes unavoidable. The system continues to exist, to function in a reduced capacity, to support some forms of life, and this continuity allows for multiple interpretations of its state. Some may see persistence and interpret it as resilience. Others may see degradation and interpret it as decline. But without a definitive moment that resolves these interpretations, the perception remains fragmented. This ambiguity makes it easier for the changes to remain outside of focused attention, not because they are insignificant, but because they do not conform to the patterns through which significance is typically recognized. The result is a reality gap, a divergence between what is happening within the ocean and what is perceived or acknowledged by those who are not directly observing it. This gap does not imply a lack of information, as data and research on these processes exist and continue to grow, but rather a mismatch between the nature of the information and the ways in which it is processed and understood. The ocean's transformation is continuous, cumulative, and often invisible in its early stages, while human attention is drawn to what is immediate, discrete, and visible. Between these two modes of change and perception, the process continues, not hidden, but not fully seen. What makes this even more difficult to recognize is that the ocean does not simply move in one direction, from life to absence, from structure to emptiness, but instead often presents something that looks like recovery, a return of color, the reappearance of movement, a surface-level signal that suggests the system is stabilizing again, and it is precisely this appearance that creates one of the most persistent misunderstandings about what is actually happening beneath the surface. After a bleaching event, when temperatures drop back into a tolerable range, some coral colonies can regain their symbiotic algae, and with that their color begins to return. Fish may move back into the area, algae may be grazed down in certain patches, and for an observer returning after a period of absence, the reef can appear to have recovered, to have survived the disturbance and resumed its previous state. This is the moment where interpretation becomes critical, because what is being observed is not necessarily a restoration of the original system, but often a reorganization into something structurally and biologically different. The coral that survives bleaching is not a random sample of what existed before. It is a subset, often composed of species that are more tolerant to heat, more resilient to stress, or simply more capable of surviving under altered conditions. This selective survival changes the composition of the reef. Species that were once dominant may be reduced or absent, while others that were previously less common begin to define the structure of the ecosystem. Over time, this shift alters not just the appearance of the reef, but its function. The complexity of coral structures may decrease. The range of habitats available for different organisms may narrow, and the interactions between species begin to reorganize around this new baseline. What looks like recovery is, in many cases, replacement. The difference between these two processes is subtle but significant. Restoration would imply a return to the previous state, a rebuilding of the same structures, the re-establishment of the same relationships between species, the recovery of the same level of biodiversity and functional complexity. Replacement, on the other hand, involves the emergence of a new configuration, one that occupies the same physical space but operates differently. In reef systems, this often manifests as a shift toward faster-growing, less structurally complex coral species, or in more severe cases, a transition away from coral dominance altogether, towards systems where algae become the primary form of life covering the substrate. These algae-dominated systems can still support life. Fish may still be present. Movement and activity may still be visible. But the underlying architecture that once supported a wide range of species is no longer there. The reef has not disappeared, but it has changed in a way that reduces its capacity to function as it once did. This distinction becomes even more difficult to detect because the process of replacement can produce visually appealing results. New coral growth can be vibrant, colourful, and seemingly abundant. Without a reference point for comparison, it is easy to interpret this as evidence of resilience, as proof that the system is capable of bouncing back from disturbance. And in a limited sense, it is resilient. The ocean is not static, and many of its systems have evolved to withstand and adapt to change. But resilience has limits, and when the frequency and intensity of disturbances increase, the capacity for full recovery diminishes. Instead of returning to a previous state, the system stabilizes at a different level, one that reflects the cumulative impact of repeated stress. Scientific monitoring of reef systems over time has made this pattern increasingly clear. Long-term studies show that even when coral cover appears to increase after a disturbance, the diversity of species often remains lower than it was before, and the types of coral that dominate are not the same. Structural complexity, which is critical for supporting a wide range of marine life, tends to decline, even if overall coverage seems to improve. This means that the reef's ability to provide habitat, to support breeding and feeding grounds, and to buffer coastlines against waves and storms is reduced, even when it appears visually intact. The system is functioning, but at a diminished capacity, and this reduction is not always immediately visible without detailed observation. There is also a temporal dimension to this illusion. Recovery takes time, but so does degradation, and when these processes overlap, they can create a dynamic in which the reef is always in a state of partial recovery from a previous disturbance while simultaneously being affected by a new one. This overlapping of cycles makes it difficult to identify a clear baseline, a stable point against which change can be measured. Instead, the system exists in a constant state of transition, and within that transition, moments of apparent improvement can mask the overall trajectory. A reef may look better this year than it did immediately after a bleaching event, but worse than it did a decade ago. Without that longer perspective, the direction of change can be misinterpreted. This is where the concept of shifting baselines intersects again with the illusion of recovery. Each observed improvement becomes a new reference point, reinforcing the idea that the system is capable of maintaining itself even as its underlying condition continues to change. The perception of recovery can also influence how these systems are discussed and understood more broadly. Reports of coral regrowth, of reefs coming back, can create a narrative that emphasizes resilience without fully accounting for the changes in composition and function that accompany it. This narrative is not necessarily incorrect, but it is incomplete. It captures one aspect of the process while overlooking another, and in doing so, it contributes to a broader misunderstanding of what recovery actually means in this context. The ocean does not simply revert to its previous state after disturbance. It adapts, reorganizes, and in many cases, simplifies. This simplification is not always immediately apparent, especially when life remains visible and active, but it represents a fundamental shift in how the system operates. Over time, as these processes repeat and accumulate, the difference between what was and what is becomes more pronounced, even if each individual step along the way seemed small, manageable, or even positive when viewed in isolation. The changes unfolding within reef systems do not remain contained within the boundaries of the ocean itself, because these structures, while biological in origin, have always functioned as part of a much larger system that extends directly into human life, shaping coastlines, supporting food systems, and quietly stabilizing entire regions in ways that are often only understood once they begin to weaken. Along tropical and subtropical coastlines, coral reefs form natural barriers that absorb wave energy before it reaches land, reducing the force of storms, limiting coastal erosion, and protecting infrastructure that has been built, often unknowingly, behind this living shield. When waves travel across open water, they accumulate energy over long distances, and without interruption, that energy is released when it reaches shorelines, reshaping beaches, damaging structures, and in extreme cases pushing water far inland. Reefs interrupt this process. Their rough, uneven surfaces break up, incoming waves, dissipating energy gradually, reducing both the height and intensity of what eventually reaches the coast. Studies have shown that healthy coral reefs can absorb up to 90% of wave energy. functioning in a way that is comparable to engineered breakwaters, but without the need for construction, maintenance, or external input. This protective function is not static. It depends on the structural integrity of the reef itself, on the height, density, and complexity of the coral formations that make up its surface. As reefs degrade, as coral cover declines and structural complexity is reduced, their ability to perform this role diminishes. The difference is not always immediately visible during calm conditions, but during storms, when wave energy increases, the absence of that natural barrier becomes more apparent. Coastal flooding becomes more severe, erosion accelerates, and the costs associated with protecting these areas begin to rise. In many regions, this shift is already being measured not as an abstract ecological change, but as an increase in infrastructure damage, insurance claims, and the need for artificial defences to replace what was previously provided by the reef. The relationship between reefs and fisheries operates on a similar principle of underlying dependence. Coral reefs support a significant portion of marine biodiversity, and within that diversity are species that play direct roles in human food systems. For millions of people, particularly in island nations and coastal communities, reef-associated fish are not a supplement to diet, but a primary source of protein. These fisheries are not uniformly industrial or large-scale. In many cases, they are local, small-scale operations that depend on the consistent presence of fish populations that use reefs as breeding grounds, nurseries, or feeding areas. The structure of the reef provides shelter for juvenile fish, increasing survival rates during early life stages, and supports a complex food web that sustains larger species as they mature. When the reef changes, when its structure simplifies or its biodiversity declines, these functions are disrupted. Fish populations may decrease, not necessarily disappearing entirely, but becoming less abundant, less predictable, and more difficult to sustain at levels that support consistent harvesting. In some cases, species that were once common become rare, replaced by others that are less desirable or less suitable for consumption. This shift affects not only the availability of food, but the stability of livelihoods that depend on fishing as a primary source of income. The economic dimension extends further into industries such as tourism, which in many coastal regions is built around the presence of healthy reef systems. Diving, snorkeling, and recreational fishing attract visitors, generating revenue that supports local businesses, employment, and broader economic activity. The appeal of these activities is closely tied to the condition of the reef. Clear water, diverse marine life, and visually complex coral structures create experiences that draw people from around the world. As reefs degrade, the quality of these experiences changes. Biodiversity declines, water clarity can be affected by increased algal growth, and the visual impact of bleached or degraded reefs reduces their attractiveness. This does not necessarily lead to an immediate collapse in tourism, but it can initiate a gradual decline, as destinations that were once known for their marine environments lose their distinctiveness. Over time, this can shift economic patterns, reducing income for communities that have come to depend on these industries and requiring adaptation to new forms of economic activity that may not be as stable or as sustainable. What makes these changes particularly complex is that they often occur without a clear point of transition. There is no single moment when a reef stops, providing protection, when fisheries become unsustainable, or when tourism declines beyond recovery. Instead, these systems adjust incrementally. Protective capacity decreases gradually, fish populations fluctuate and trend downward over time, and economic impacts accumulate across seasons and years. This gradual nature makes it difficult to attribute specific outcomes directly to reef degradation, even when the connection is present. A storm causes more damage than expected, but storms vary in intensity. Fish catches decline, but fishing practices and environmental conditions also change. Tourist numbers shift, influenced by a range of factors beyond reef health. Within this complexity, the role of the reef can become obscured, even as its influence remains significant. Long-term data and comparative studies provide a clearer picture of these relationships. Coastal areas with intact reef systems consistently experience lower levels of wave-driven damage compared to those where reefs have degraded. Fisheries associated with healthy reefs show greater stability and productivity over time, while those linked to degraded systems tend to exhibit more variability and decline. Tourism revenue correlates with reef condition, not only in terms of biodiversity but also structural complexity and visual appeal. These patterns indicate that reefs function as foundational components within these human systems, supporting processes that extend far beyond their immediate physical boundaries. The loss or alteration of these systems does not simply remove a single element, but initiates a series of adjustments across multiple layers of interaction. As these adjustments accumulate, they begin to reshape the way coastal regions function, influencing everything from infrastructure planning to food security and economic development. The connection between reef systems and human systems is not always visible in daily life, particularly for populations that are geographically distant from these environments. However, for communities that exist in close proximity to reefs, these changes are experienced more directly, often as shifts in conditions that were once stable and predictable. The broader implication is that the processes affecting reefs are not isolated ecological events, but part of a larger transformation that intersects with human systems in ways that are measurable, cumulative, and increasingly difficult to ignore when viewed over extended periods. When these changes are placed within a longer timeline, a different kind of tension begins to emerge, not from what is immediately visible, but from the mismatch between how quickly the system is being altered and how slowly it is capable of rebuilding itself. Coral reefs are not fast systems. The structures that define them, the layered skeletons that create habitat and complexity, are built incrementally, often over decades and centuries. Some of the largest reef formations on Earth are the result of continuous growth across thousands of years, each generation of coral adding a thin layer to what came before, gradually constructing the architecture that supports entire ecosystems. This pace is fundamental to how reefs function. It allows for stability, for the development of intricate relationships between species, and for the accumulation of complexity that cannot be replicated quickly. When disturbance occurs, recovery follows the same timeline, even under favorable conditions. Coral regrowth is measured in millimeters to centimeters per year, depending on the species. The re-establishment of a fully functional reef, with its original diversity and structural complexity, can take decades at a minimum, and often much longer. This would not necessarily be a problem if disturbances were rare, if the system had time to recover fully before being challenged again. But the current pattern does not allow for that kind of recovery window. Ocean temperatures are rising at a rate that introduces stress events more frequently than in the past. Bleaching events that were once separated by decades are now occurring within years of each other in many regions. This compresses the timeline, forcing reefs to attempt recovery while still under pressure, never fully returning to a stable baseline before the next disturbance arrives. The result is a gradual erosion of resilience. Each event removes a portion of the system's capacity to respond, and over time that capacity, diminishes to a point where recovery becomes incomplete or fails entirely. This is where the idea of a point of no return begins to take shape, not as a single clearly defined moment, but as a threshold that is approached gradually and crossed without a clear signal. In many systems, tipping points are associated with abrupt changes, a sudden shift that marks a transition from one state to another. In reef ecosystems, the process is often more ambiguous. The system can continue to function in a degraded form, maintaining some level of coral cover, supporting some level of biodiversity, even as its underlying structure and resilience decline. From the outside, it may not be obvious that a critical threshold has been crossed. The reef is still present, life is still visible, and yet the capacity for full recovery may already be lost. Scientific research attempts to define these thresholds, to identify the conditions under which reefs can no longer sustain themselves in their current form. This involves understanding the relationship between temperature, frequency of bleaching events, water chemistry, and other stresses such as pollution and overfishing. Models can estimate the likelihood of recovery under different scenarios, projecting how reefs might respond to continued warming or changes in local conditions. These models suggest that beyond certain temperature increases, often in the range of 1.5 to 2 degrees Celsius above pre-industrial levels, the frequency of severe bleaching events becomes so high that most coral reefs cannot recover between disturbances. Under these conditions, the system shifts toward a new state, one that may still include some coral, but lacks the diversity and structural complexity that define healthy reefs. However, these thresholds are not precise boundaries. They vary depending on local conditions, species composition, and the interaction of multiple stressors. Some reefs may exhibit higher tolerance, influenced by factors such as water flow, depth, or the presence of more heat-resistant coral species. Others may be more vulnerable, reaching critical points at lower levels of stress. This variability introduces uncertainty, making it difficult to identify a universal point at which reefs are considered irreversibly changed. It also means that different regions may cross these thresholds at different times, creating a patchwork of outcomes across the global ocean. In some areas, reefs are already considered functionally lost, not in the sense that all life has disappeared, but in that they no longer perform the roles that define them as reef systems. Coral cover may be minimal, structural complexity reduced, and the associated biodiversity significantly diminished. In other regions, reefs remain more intact, but are increasingly exposed to conditions that place them at risk within the coming decades. The trajectory is not uniform, but the direction of change is consistent. What complicates this further is that the crossing of a threshold does not produce an immediate visible signal that can be easily recognized. There is no clear marker that indicates the system has passed a point beyond which recovery to its previous state is no longer possible. Instead, the recognition often comes retrospectively, through long-term observation and comparison, when it becomes evident that the system is no longer returning to its earlier condition, despite periods that appear favourable. This delay between crossing a threshold and recognising it creates a gap in perception. By the time the change is fully understood, it may no longer be reversible within human timescales. This does not mean that all change is irreversible, or that all reefs will follow the same path. It means that the process of change includes stages that are not immediately identifiable as critical, and that the absence of a clear signal does not indicate the absence of a threshold. The system can move from one state to another through a series of incremental steps, each one appearing manageable or even negligible on its own, but collectively leading to a transformation that is difficult to reverse. In this context, Uncertainty is not simply a lack of knowledge, but a fundamental characteristic of how these systems behave under stress. It reflects the complexity of the interactions involved, the variability across different environments, and the limitations of observing processes that unfold over long periods. The challenge is not only in understanding where these thresholds lie, but in recognizing that they may be crossed without clear indication, embedded within the gradual changes that define the system's response to ongoing pressure. When all of these pieces are placed together, not as isolated events or separate explanations, but as parts of the same system unfolding over time, the picture that emerges is not one of sudden disappearance, but of continuous transformation, a shift that does not announce itself in a single moment, but instead unfolds through small cumulative changes that gradually alter the structure of the ocean itself. The expectation of collapse, as it is often imagined, involves a clear break, a before and after that can be easily identified, a moment where a system fails in a way that is visible and undeniable. But the reality that has been developing across reef systems does not follow that pattern. There is no single event that defines the transition, no clear boundary where the ocean can be said to have crossed from one state into another. Instead, there is a sequence of adjustments, each one building on the last, each one reducing a small part of the system's complexity, until the overall structure begins to resemble something fundamentally different from what existed before. Life does not disappear in this process. It persists, adapts, reorganizes. Fish continue to move through the water, algae continues to grow, microbial systems continue to function. The ocean remains active, dynamic, and in many places still visually rich. This persistence is part of what makes the transformation difficult to recognize. The presence of life creates a sense of continuity, a perception that the system remains intact, even as its underlying composition changes. But what is being lost is not simply the presence of organisms, it is the arrangement of relationships between them, the layered interactions that create stability, resilience, and the capacity for complexity. Coral reefs, as they once existed, are defined by this complexity. They are systems where countless species interact across different scales, where structure creates habitat, habitat supports diversity, and diversity reinforces the stability of the system as a whole. When that structure begins to erode, when the physical architecture becomes simpler, the number of available niches decreases, and with it, the range of species that can be supported. This reduction does not eliminate life, but it narrows it. Fewer species dominate, interactions become less intricate, and the system becomes more uniform. In ecological terms, this is a shift from a highly complex, multi-layered system to one that is simpler, more homogeneous, and often more vulnerable to further change. This pattern is not unique to coral reefs. It reflects a broader principle in ecological systems, where complexity is associated with stability, and simplification often leads to increased susceptibility to disturbance. In the ocean, this simplification is occurring in ways that are not always immediately visible, but can be measured through changes in species diversity, biomass distribution, and the structure of food webs. Predatory species may decline, altering the balance of lower trophic levels. Herbivorous fish that once controlled algal growth may become less abundant, allowing algae to expand. Microbial communities may shift in response to changes in water chemistry, influencing nutrient cycles and the overall functioning of the ecosystem. Each of these changes represents a small adjustment, but together they redefine how the system operates. What makes this transformation particularly significant is that it alters not only the present state of the ocean, but its future trajectory. A system that has become simpler is less capable of supporting the same level of biodiversity, less resilient to additional stress, and less able to recover to its previous state. The pathways that once allowed for regeneration and complexity become narrower, and in some cases may no longer exist within the current conditions. This does not mean that the ocean will become empty, or that life will cease to exist within it. It means that the form that life takes, the structure of the systems that support it, and the functions those systems perform are changing in ways that are cumulative and directional. The idea that the ocean is dying can be misleading if it is interpreted as a process of total loss. What is occurring is more accurately described as a reconfiguration, a shift from one state to another, driven by a combination of temperature change, chemical alteration, and repeated disturbance. The language of disappearance does not fully capture this process, because it suggests an endpoint that is clearly defined, a moment when the system is gone. In reality, the system continues, but in a different form. This distinction matters because it influences how the change is perceived and understood. If the expectation is of a sudden collapse, the absence of that collapse can be interpreted as evidence that the system remains stable. But if the process is understood as gradual transformation, then the same observations take on a different meaning. The presence of life, the appearance of recovery, the continuation of activity do not necessarily indicate that the system is unchanged. They may instead reflect the ongoing adaptation of that system to new conditions, conditions that favor different forms of life and different structures of interaction. Over time, these adaptations accumulate, and the difference between the past and the present becomes more pronounced, even if no single moment marked the transition. This is why the changes can pass largely unnoticed, not because they are insignificant, but because they do not align with the way change is typically recognized. They do not produce a single, defining event, but instead alter the baseline against which all future observations are made. Each generation inherits a version of the ocean that reflects the cumulative changes of the past, and within that inherited baseline, the current state appears normal. The transformation becomes embedded within the definition of what the ocean is, rather than standing out as a deviation from it. In this way, the process is self-concealing. The more it progresses, the more it redefines the expectations that would allow it to be recognized. The ocean is not disappearing in a way that can be easily observed or measured in a single moment. It is becoming something else, something that retains many of its visible characteristics, but operates with a different structure, a different level of complexity, and a different capacity to support the forms of life that once defined it.